All right, welcome to lecture 12 for ECE 203. Today we're going to continue our discussions of the discrete Fourier transform, or the DFT. All right, and what we have written on the screen kind of the two important equations that we need to know about the DFT. So the first one is really just how we, given the DFT coefficients, those are written as capital X of k, that's shown in green, right here. Given those coefficients, how would we represent the signal x of n? And it's just those coefficients tell us the weighting of these complex exponentials such that when we add all of these terms together that we get back to the original, the signal x of n. All right. So we looked at that a lot last time, and then written immediately below that is the equation for how we calculate these x of k's. If we're given x of n, if we're given the discrete time signal x of n, and it has some length capital N, then we can calculate these x of k's. And the x of k's somehow tell us the amount of energy that's kind of correlated to a particular complex exponential at a frequency of k over n, at a digital frequency of k over n. So it really tells us kind of the energy, the amount of energy that's at a particular frequency. Right, at a particular digital frequency. And these capital X of k or uppercase X of k, these are denoted, these are called the DFT coefficients. So when somebody, if we were asked to find the DFT of a signal x of n, we would just compute these X of k's. And what we're going to do in this lecture today is we're going to talk a little bit more about how we can relate these back to the Fourier series, which we saw for continuous time signals. We can look at these basic sinusoidal building blocks, kind of interpret things that way, and then this will allow us to kind of draw the spectrum of any discrete time signal x of n, right? And when we draw the spectrum, right, we're really just plotting on the horizontal axis frequency. So in this case, we'll look at digital frequencies. That'll be plotted on the horizontal axis, and then kind of the amplitude will be the absolute value of this x of k. Right? That kind of tells us how much energy in the original signal x of n is at a particular digital frequency k over n. So last time, remember, we really briefly talked about another way to write the DFT, and that's just in terms of summing up. Instead of using these complex exponentials, we can just sum up cosines, right? Or the cosines are again at these same frequencies, k over n. Now this is slightly different than the Fourier series, right? Because Fourier series, this upper limit in the sum, that was infinity. So here we only need a finite number of terms. Okay? And the number of terms, I'm assuming capital N is odd, just to make things a little easier, is n minus 1 over 2. So for example, if capital N were 11, then the sum would have 5 terms in it. So let's just see these basic sinusoidal building blocks. Okay? And we'll see they're sinusoids at different frequencies. And let's use that same example where capital N is 11. All right, so these are plots of the basic sinusoidal building blocks, like I mentioned, for the DFT coefficients. So what the DFT is doing is it's taking each one of these sinusoids, it's weighting it by some amplitude A, okay? Weighting it by some amplitude A, and then it's also giving it some phase shift, and then it's adding all of these together to give you x of n. So the frequencies of these discrete time sinusoids, the first one is at a digital frequency of 0, right? So that's k equals 0, so it's at digital frequency of 0. The second one's at a digital frequency of 1 over capital N, where here n is 11, right? And if we go back, that comes from, of course, down here. These are where the digital frequencies are, this k over n, right? So we can keep looking at all of these. We see as k increases, the digital frequency increases, right? It's just harmonics of this. You can think of this as the fundamental frequency, 1 over n, and then we have harmonics at 2 over n, 3 over n, 4 over n, and these are digital frequencies, right? So the units of these is cycles per sample. And at the end of the day, when we give each one of these basic sinusoidal building blocks some amplitude and some phase shift. The idea is we're going to add them all up, and that'll give us back our original signal x of n. Okay, so that's just kind of one way to interpret the DFT. And what's important here is this amplitude, for example, A2, that tells us how much energy is at a digital frequency of 2 over 11. So we can interpret this as the spectrum of the signal x of n. So that's what I want to talk about next, and that's how do we use the DFT to compute the spectrum. All right. So I've written again the equation for calculating uppercase x of k, for calculating the DFT coefficients. Let's look at this again in a little more detail. So we're summing from k equals 0 to n minus 1. Right? We're summing over all the values of x of n, and each sample of x of n is weighted by a complex exponential, right? At a digital frequency of k over n. All right, and this equation is again now for k equals 0, 1, 2, all the way up to n minus 1. And evaluating this kind of correlates the signal with, think of it as correlating it with a complex exponential, and it tells us kind of the amplitude and the phase of each of these sinusoidal building blocks, right? So x of k is in general, this is going to be a complex number, and so that gives us an amplitude and the phase, the corresponding sinusoidal building block. And then we can take these values of x of k and we can just plot these as the spectrum, right? Because as I said, this kind of tells us the amount of energy that's at a particular digital frequency, k over n. So what I have plotted here is exactly that. So on the vertical axis is just x of k. On the horizontal axis, I've just plotted k. And what I would do here is I would kind of write these out. So just for integers, right? K only takes values 0, 1, 2, 3, dot, 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 out to n minus 1. And then you could just plot the corresponding value of capital X of k. So we can interpret that as a spectrum, right? Just like we interpreted the spectrum just like we interpreted the Fourier series as the spectrum. And again, I'll say the main idea here is that x of k is the weight given to the sinusoidal building block, e to the j 2 pi k over n times n, right? So at a digital frequency of k over n. And so each one of these weights corresponds to this digital frequency k over n, and that's in cycles per sample. All right, so we're almost there. We're close to interpreting this as the spectrum of the signal. So let's kind of just look at that in this way. So again, I rewrote the equation for x of n up here. Once we have these coefficients, how do we get x of n? And we can see here the way we do that is we take these DFT coefficients, multiply them by the complex exponential k over n, and then we add them all together. So that's telling us how much of the signal is at the digital frequency capital K over n. So all I've done now is I've plotted this horizontal axis in terms of f hat, in terms of the digital frequency, and of course this value capital X of 0, that's at a digital frequency of 0 cycles per sample, and the next value, which would be capital X of 1, that's at a digital frequency of 1 over n cycles per sample, and so on. So now let's note here what's changed from the last plot to this one is now instead of just having 1, 2, 3 here, which was just the index, which was just k, we've now plotted f hat. All right. So if we were to just take the absolute value of the DFT coefficient x of k, that would just tell us kind of how much energy is at that digital frequency of k over n. And now this looks a little different than the spectrums that we plotted before, right? And I guess the reason it looks different is because we've plotted, now before we saw there were always these matching negative frequencies. And this is just kind of by convention. And the reason that we'll see these are actually equivalent is just notice that the following is true. So if I look at these, for example, the coefficient that's way out here at a digital frequency of n minus 1 over n, right? I can write that corresponding complex exponential is written here. E to the j 2 pi n minus 1, that quantity over capital N times n. And then I can just kind of factor out that n over n term, that's just 1. So that'll give me e to the j 2 pi n multiplied by e to the minus j 2 pi 1 over capital N times n. So what do we notice here? Well, this is just 1, right? That's 1 for all values of n. So what this is saying is these bigger frequencies up here, these guys, those are really equivalent to negative frequencies, right? So in particular, this guy is equivalent to, we can just draw him. So the frequency n minus 1 over n, we can just draw that at a frequency of minus 1 over n, right? And then, of course, we could do the same thing for the next frequency. This would be this frequency of n minus 2 over n. We can write that as just minus 2 over n. Just in the same way that we calculated this out, we can do that for all of these guys down to about halfway. So these bigger frequencies, they really just correspond to negative frequencies. Right? And this is, we kind of saw this in lab, because when we ask MATLAB to compute the FFT of a signal, it really gives it to us in this form up here, right? Where k goes from 1 to n. But we can then use that command FFT shift. We saw this in lab, and then we can get a spectrum like the one that's written here. Right. So the two things are really actually equivalent.